over here, and this is the 1998 AIME Problem 13. Here's a view of this problem. If this set is a set of real numbers indexed such that a sub 1 is less than a sub 2 is less than a sub 3, which is all less than a sub n, its complex power sum is defined to be a sub 1I plus a sub 2I squared plus a sub 3I cubed, all the way until a sub n I raised to the power of n. Let S sub n be the sum of the complex power sums of all non-empty sets of 1, 2, all the way until n. So given that S sub 8 is equal to negative 176 minus 64i, we wish to find S sub 9. Okay, so let me try to digest this problem. So for any subset a1, a2, a3, all the way until an, we choose a certain subset. And then for that certain subset, we do this complex sum over here to get that certain complex sum. And then we essentially sum over for all the subsets to get our complex number sum for the total thing. And we're given that for 8 is equal to negative 176 minus 64i. So now the natural question is, how do we get from S sub 8 to S sub 9? So S sub 8 will consider everything 1, 2, 3, 7, 8, right? So basically all we're doing for S sub 9 is we're considering S sub 8 cases, except we have a 9 appended to it. So basically if we exclude the 9, we basically get S sub 8. So S sub 9 is equal to S sub 8. Now what happens if we do have a 9? If we do have a 9, well, we're automatically including 9 in, and then we get another S sub 8 case. So another S sub 8 case. The only difference is now that we have a 9, and we know since because of this indexing rule, it's going to be the last term. So we need to have 9i raised to the power of x, where x is essentially the cardinality of our subset. Great. So S sub 9 is equal to 2s sub 8 plus 9i raised to the power of x, where x is simply our cardinality. So how do we deduct 9i raised to the power of x? 9i raised to the power of x. Well, x could simply be singleton, in which case it's just the 9. So 9 is already added. There are 8 choose 0, ways to choose remaining elements, and then we simply multiply by 9i raised to the power 1. And then this is if x is equal to 1. How about if x is equal to 2? If x is equal to 2, 9 is already added, so we need to choose one element from the remaining 8. 8 choose 1 ways to do that. And then now we need to do 9i raised to the power of 2, right? If x is equal to 2. And then how about let's just do for x, if x is equal to 3. If x is equal to 3, same thing's happening. Choose 2 elements, 9i raised to the power of 3. All the way until, well, we could choose all the 8 elements, in which case the subset is the set, this whole set. In which case we have a choose a, which is trivially one way to choose everything. And then we need to append a 9i raised to the power of 9, right? 9, yep. So can we make this more rigorous using summation notation? And the answer is yes. So note that we're going from 0, 1, 2 all the way until a. So that motivates maybe a bounds of k is equal to 0 to 8. And then now what happens is we're going to have a 9. First let's deal with the choose condition. We are going to have an 8 choose k over here. And then times I. And then now this x will just be k plus 1, right? For everything, x is just k plus 1. So we wish to evaluate this summation. And that'll give us our 9i raised to the power of x, summed for every subset. Okay. How can we do this? Oh, I forgot a 9. So maybe we can rewrite this as, there's actually a beautiful way to do this without having to resort to doing this with hand, because that'd be painful. 0 to 8, and then this just becomes 9i times a choose k times I raised to power k. Now for this one, this is just a binomial expansion for 1 plus I raised to the power of 8, right? And then, so this just becomes k equals 0 to 8 of 9i times 1 plus I raised to the power of 8. Because if this is like the binomial expansion for 1 plus I raised to the power of 8. And now we're in familiar territory. None of this depends on case, so it just suffices to evaluate this. Instead of using the binomial theorem for this, we'll just resort to De Moivre's theorem. This can be written as root 2 cosine 45 plus I sine 45. Okay, and then we're raising this to the power of 8. We do root 2 raised to the power of 8, which is just 2 raised to the power of 4, which is 16. And then distributing the 8 over, because that's what we do with the Moivre's formula. Again, I encourage you to try to prove that using induction. That becomes cosine 360 plus I sine 360. This cancels away. This becomes 1. So 16. So this whole thing evaluates to 144i. Now that we know this is 144i, we can go about evaluating S sub 9. S sub 8 is what? This. So if we are to do 2 times S sub 8, that becomes negative 352 minus 128i. And now all we're doing is adding a 144i to get our final answer. Let me just make sure I did, yep. Okay, and then adding, we get negative 352 plus 16i. Okay, we found S9, P and Q are integers. We want to find the absolute value of P plus absolute value of Q. That becomes 368, and we are done.